This is where we left off class on Thursday before we got redirected to online. We were speaking about glycolysis, and we had looked at the pathway of glycolysis and the relationship between glycogen and where it fits in that pathway. And what you can see with the glycogen arrow is that glycogen enters the pathway as glucose 6-phosphate. What this means is that glycogen requires one less ATP in order to run the process of glycolysis and produce 4 ATP. This gives us a net yield of 3 ATP when we begin with one glycogen molecule compared to 2 ATP when we begin with one glucose molecule. Now this is important to know for several reasons. Number one, if you are an athlete or an individual engaged in very high intensity, high volume training, where your training bouts are rather frequent. Maybe you have a morning practice and an afternoon or evening practice. It's 2-a-days at the start of a season for soccer or for football. Well, if you don't replenish glycogen by consuming carbohydrates and instead try to rely on increasing your blood glucose before that activity, you're not going to be producing ATP as efficiently, and you are going to probably fatigue sooner. Now it also requires about 22 to 40 hours to fully replenish glycogen if you fully deplete it. You're not going to fully deplete it over the course of a 1-hour practice, but you are going to deplete it enough such that it's going to affect your performance. To recap, glycolysis is stimulated by the byproducts of the phosphagen system, those being creatine, ADP, and adenosine monophosphate. It's a little more complex process. It requires about 12 to 13 steps before ATP is produced. If we use blood glucose, we produce 2 ATP. When we use muscle glycogen, we produce 3 ATP. And if we look at the graph to our right, we can see called the lactic acid system in that graph. It's the green line. You can see that after a few seconds we start to begin producing ATP with that glycolysis, with that lactic acid system. And then we reach a threshold somewhere around 45 seconds. And at that threshold you can see ATP production falls off dramatically. That threshold occurs when hydrogen buildup, when acidity within the cell has reached some sort of threshold level that inhibits the production of more ATP via glycolysis. Now, if you are doing some sort of repeated effort, longer or repeated efforts over a prolonged duration, right? Like you're running repeated 400-meter sprints, maybe doing 10 of them, or a typical team sport practice, stop and go, a lot of sprinting, a lot of conditioning. So something that lasts about 45 minutes to an hour, then not only could hydrogen be the cause of fatigue, but inadequate carbohydrate availability could start to cause fatigue. So that could be due to glycogen depletion or beginning to deplete glycogen, or it could also be due to inadequate carbohydrate consumption. There was a time back in, I want to say, 2010 maybe, when the Lakers hired a nutritionist who was very big on keto and the paleo diet. And she had her athletes consuming nuts and beef jerky as their pregame meal. They were eating a very low carbohydrate diet. And although some of them felt better, their performance was significantly affected. You could tell that they were fatiguing. The reason why they felt better is because the likes of Dwight Howard was consuming, I think it was like the equivalent of 26 Snickers bars worth of sugar per day. So if you're not consuming enough carbohydrate, then this could also lead to fatigue when using this system. So we're looking at 20 to 45 seconds of all-out work for most individuals. Maybe a minute to a minute and a half in people who are really conditioned. And this is with a substantial period of rest in between, like 10 minutes of rest in between. Or we're looking at repeated bouts of high intensity work with work to rest ratios of 1:1 to 3:1. So run for 30 seconds, rest for 30 seconds. Or run for 15 seconds, rest for 15 seconds. Or run for 45 seconds, rest for 15 seconds. Or run for 15 seconds, rest for 5 seconds. I think you get the point. These are slightly longer periods of work than we would use in the phosphagen system and much shorter periods of rest. So some examples, most of your team sports, cross, your longer sprints, 200 meters to 600 meters. Basketball, another stop-and-go sport. Soccer, another stop-and-go sport. Our last energy system to cover is the oxidative energy system, sometimes called the aerobic system. In a nutshell, there are 3 steps to producing energy oxidatively. The first step is preparation. And this is where we're breaking down substrates to produce the molecule acetyl-CoA. So during glycolysis, we break down glucose and glycogen, we produce pyruvate. If the rate of ATP production is on the slower side, then that pyruvate is going to be brought to the mitochondria, converted to acetyl-CoA, it's going to enter the Krebs cycle. Beta-oxidation is the process of breaking down fats into acetyl-CoAs so that we can run them through the Krebs cycle. The Krebs cycle takes place in the mitochondria, and essentially what it is the removal of energized particles, hydrogens and electrons. Notice that we still haven't used oxygen yet. We still haven't created any ATP yet. Finally, we have oxidative phosphorylation, or the electron transport chain. And this is when we use the energy of those hydrogen molecules and electrons that were removed during the Krebs cycle, and we use them to rebuild ATP. Our final product is going to be ATP and water. Here's the Krebs cycle in a little bit more detail. So it's a cyclical process of removing energized electrons. Acetyl-CoA enters the Krebs cycle. It merges with oxaloacetyl acetate, creating a 6-carbon molecule of citric acid. That molecule is then passed from enzyme to enzyme to enzyme. And as it's passed around the cycle, it's slightly altered. And so what you can see is carbon dioxide is removed. So we go from 6-carbon molecule to a 4-carbon molecule. We produce 1 ATP, but what we also produce is a lot of these energized particles. So we produce 3 NADH and 1 FADH for each acetyl-CoA that enters the Krebs cycle. In this next video, we're going to look at the mitochondria, a cross-section of it in a little more detail, and see what exactly is happening in that electron transport chain to allow us to produce ATP. We have the mitochondria. If we look at it, if we take a slice of it and look within the mitochondria, it's a couple important structures to point out before we start talking about what's happening and how we're making ATP oxidatively. This structure here is the outer membrane. This structure here is the inner membrane. This structure is the intramembranous space between the 2 membranes. On the inside, it's called the matrix. Going on within the mitochondria, it's going to be the Krebs cycle. Acetyl-CoA enters the Krebs cycle, is transformed, carbon dioxide is produced, it exits the mitochondria. Within here, in the Krebs cycle, we produce hydrogens and electrons. Those hydrogens and electrons are carried by NADH, and FADH. Electrons from NADH are passed on to complex 1. Electrons then pass from complex 1 to molecule 2, to complex 2, to complex 3, to cytochrome C, to complex 4. Those are the electrons. The electrons are negatively charged. The hydrogens, which we'll draw in red, are positively charged. And these complexes use the difference in charge to pump the hydrogens out. What this does is it creates a huge gradient where there are a lot of hydrogens in this intramembranous space. You get the point. Imagine they circle all around. So what we have is a concentration gradient. Lots of hydrogens in the intramembranous space, very few hydrogens in the matrix. Molecules always want to move from an area of higher concentration to an area of lower concentration. So imagine these hydrogen molecules are like people on an elevator. They're all crammed into each other. They're bumping into each other. Someone has bad breath. This one has a farting baby. This one has a crying baby. They are very unhappy. And they are stuck here. Now imagine you're on that elevator. How do you feel? You're stuck in between the person with bad breath, the farting baby, and a guy who wants to talk to you about politics. You want to get the hell out of there. So do these hydrogens. Well, we allow them to come back inside into the matrix through a molecule called ATP synthase. As those hydrogen molecules rush through that ATP synthase molecule, they turn this wheel. That kinetic energy is captured and utilized to rebuild ATP. Now, we're not done yet, because if these hydrogens just keep coming through from the intramembranous space into the matrix, at some point we're going to reach an equilibrium. There's going to be a similar concentration here to out here. These hydrogens out here are going to look inside and see all those other hydrogens and be like, nah, I don't want to be around those. Nah, it's just as good out here. Then we don't produce ATP, and then you die. Here's where the oxygen comes in. This complex 4 holds on to an oxygen molecule. We'll call this oxygen molecule this blue here. And what it does is it combines two hydrogens with that oxygen to form water. And this water diffuses out of the cell. And now we maintain our gradient. Hydrogen gets pumped out, big concentration gradient, rushes in through the ATP synthase. The movement of it rushing in turns this wheel almost like you walking through a turntable or a push door into a mall. As it does so, that energy is captured, used to rebuild ATP. So as long as we have an adequate amount of oxygen within the matrix, this process can continue for a very long time. In fact, it's happening right now to provide you with ATP to carry out all your bodily functions while you are watching this lecture.
Here's another look at the electron transport chain in a little more detail of just the chain and what is happening. You can refer back to this in your notes. So in brief, in terms of the aerobic system or oxidative phosphorylation, we use glycolysis to produce pyruvate and to produce 2-NADH. That pyruvate can then enter the Krebs cycle. Because each glucose produces 2 pyruvates, then we send a total of 2 acetyl-CoAs through the Krebs cycle. In doing so, we produce 6-NADH, 2-FADH, another FADH as we convert the pyruvate into acetyl-CoA. Those hydrogens and electrons are then transported, the electron transport chain. As they're passed down the chain, their energy is captured and used to produce ATP. So from a single molecule of glucose, if we finish the process aerobically, we can produce 36 ATP. The downside to this is all these steps take a while to occur. So we can't produce ATP rapidly like we can if we finish off glycolysis by producing lactate. The upside is hydrogen is no longer a concern because we're combining it with oxygen to form water. And so we can do this process almost indefinitely. If we're doing it with fats, fats are a chain of carbon molecules. Generally, the fats that we consume in our diet are about 10 to 20 carbon molecules, and they're always an even number. So the process of beta-oxidation is chopping off 2 carbons at a time. Those 2 carbon molecules are chopped off at a time, as you can see at the top where it says beta-oxidation and that blue arrow. And they enter the Krebs cycle as acetyl-CoA. So for a typical 16 carbon chain of fat, we can produce 8 acetyl-CoA. In doing so, we can produce quite a bit of NADH and FADH. And so for not a single molecule of triglyceride, the fats that we eat in our diet, but for one single fatty acid, the triglyceride is a glycerol molecule, 3 fatty acids. So for one single fatty acid, we can produce over 100 ATP. The downside to this is it happens real slow, and it requires more oxygen to produce the same amount of ATP compared to carbohydrates. So this is our least powerful way of producing ATP. In other words, we produce ATP at the much slowest rate. So we use this oxidation of fats during most resting activities and very low intensity activities when we don't need to produce ATP at a fast rate. And then the faster we need to produce ATP, the further up we go in the ladder of energy production, to aerobic glycolysis, to anaerobic glycolysis, and if necessary, the phosphagen system. And you can see the aerobic system in the dark blue in the bottom. And what you can see is it takes a couple minutes before we can start producing ATP at our maximal rate for that system. You can also see that that maximal rate is much less than that for anaerobic glycolysis, that green line labeled as lactic acid system, and much less compared to the phosphagen system, that purple line. But what we can also see is that we can do this for several hours. In fact, we can use this system with carbohydrates for about 2 to 4 hours before we deplete all of our glycogen. So it's got a slow rate of energy production, but a limited capacity to make ATP as long as oxygen is present. What are some examples? Long distance swimming, cycling, triathlons, long distance running, those kind of things. Your typical endurance sports. Sports that are continuous in nature, of a relatively steady speed the entire time, and occur for a prolonged period of time. Let's fill in these blanks. So here we have our 4 systems: the phosphagen system, anaerobic glycolysis, the oxidation of glucose, so aerobic glycolysis, and the oxidation of fat, Beta-Oxidation. Our substrates for anaerobic glycolysis, write this down, complete this chart, it's going to be very useful, are glucose and glycogen. Our products are lactate. If we imagine that the phosphagen system has the highest rate, then anaerobic glycolysis can produce ATP at about 55% of the speed of the phosphagen system. Our duration for anaerobic glycolysis is about 45 seconds all out, or very short periods of stop and go with incomplete rest. And the cause of fatigue, as you very well know, is going to be the accumulation of hydrogen, so intracellular acidosis. We oxidate glucose. Again, we begin with glucose or glycogen. The products are going to be carbon dioxide and water. You can see when we are metabolizing glucose aerobically, we can produce ATP at about 1/4 the rate in which we can produce ATP with the phosphagen system. So we can produce about 25% of the power. Our duration is going to be about 2 to 4 hours, and our cause of fatigue is going to be the depletion of glycogen. Then lastly, we have the oxidation of fats, so fatty acids. Products are also going to be carbon dioxide and water. Our duration here is days. Humans store enough fat to power them for, in some cases, months on end. Perhaps you've watched Naked and Afraid, where they don't eat for the first 2 weeks. So we can oxidate our stored fats for a prolonged period of time. And the cause of fatigue here is, well, you're probably going to die before you run out of all your fats. Now you saw on this previous slide how it takes a couple minutes before we start using aerobic metabolism. Those couple of minutes it takes you can think of as spooling up. And so imagine we're running a 5K. It's going to take us a little bit of time before we get to our steady state oxygen consumption. So in the upper left corner of this box, this purple shaded area, we are producing energy anaerobically. What is happening in that time? Well, our heart rate is increasing. Our rate and depth of respiration is increasing. Essentially, it's taken us a couple minutes to transport oxygen and enough oxygen to the mitochondria of our muscle cells where we can produce all the ATP we need aerobically. So we run, we've reached our oxygen requirement, the race ends. And if you've ever raced, or on Tuesday, hopefully, weather permitting, when you do race a 5K on the track, you'll see that at the end, you're still breathing heavy. Why are you breathing heavy? Well, this is called the excess post-exercise oxygen consumption, or the EPOC. This is the recovery period after exercise. And in this recovery period, our aerobic system is working a little bit harder than it would at rest. What is it doing? Well, it is clearing lactate. Right? Lactate is being transported to the liver, where it's undergoing gluconeogenesis and being converted back to glucose. We're clearing acid, so all those hydrogen molecules that we produced at the start of the race, we need to buffer them and excrete them. We also need to excrete other metabolites like urea. We're also replenishing fuels. We're rebuilding ATP, we're rebuilding phosphocreatine, and we're rebuilding glycogen, especially if you've consumed some carbohydrates after that exercise. To a lesser extent, we're allowing for cardiovascular recovery, so for our heart rate to come back down, to expel any heat that we may have accumulated, and to metabolize some of the hormones that were produced during exercise. So that's called the EPOC period. It's the recovery period.
So for single event activities, like a 400-meter sprint seen here, the anaerobic system is going to provide most of the ATP rapidly during the work, and the aerobic system is going to rebuild it. So here we have about a minute of exercise. So if you're really, really fast, you've ran a lap around the track. You've ran 400 meters. At the end of that minute, you're still breathing heavy for quite a while. And you're doing so as part of the EPOC. Imagine we do a bunch of them. Each time we do this, our EPOC is going to be a little bit higher than the last time. And the more intense the bout of exercise, and the more than we do, the greater our EPOC is going to be. So this is why high-intensity interval training is effective for reducing fat mass. You may not burn as much calories during the actual exercise, but your metabolic rate is going to be elevated for a period of time afterwards. Certainly a lot more than getting on an elliptical and going at a very moderate pace for an hour. One more video. We're going to look at exactly how we rebuild fuels. Specifically, the fuels of the phosphagen system.
Here we see the relationship between anaerobic work and aerobic recovery. This anaerobic work specifically occurring through the phosphagen system. So imagine we have a game of football. You're a defensive lineman. The ball is snapped. You rush the passer. You're working really hard. You're trying to break through the offensive line to sack the quarterback. A typical play in football lasts about 4 to 5 seconds. While that play is occurring, while you're trying to sack the quarterback, creatine phosphate is being catabolized. The energy is being captured and being used to rebuild ATP. That ATP is then supplying the contractile filaments so that they can produce a high amount of force so that you can accomplish your task. The whistle blows, the play is over. What we are left with is a lot of ADP and a real lot of the byproduct, that plain old creatine. You now have 40 seconds before that whistle blows and you need to try and sack the quarterback again. Here is where the recovery takes place. You walk back to the huddle, you're breathing heavily. That additional oxygen you're breathing in is being used to make ATP. Except that ATP is not being transferred directly out into the cell. Instead, that ATP is being used to provide the energy to rebuild creatine back into creatine phosphate. That way, when you break from the huddle, you go back to the offensive line, the ball is snapped, you have plenty of creatine phosphate to provide the high-intensity energy that you need for those next 4 to 5 seconds to produce a very tremendous amount of force to try and sack the quarterback. And so having a developed aerobic system is important for athletes, individuals who are performing repetitive, high-intensity tasks. During the recovery period, the more developed your aerobic system is, to an extent, obviously if you train exclusively to develop your aerobic system, you're going to lose all these abilities to generate a lot of force. But the more developed your aerobic system is, the faster that you can create ATP, and the faster you can use that ATP to replenish creatine phosphate so that when it's time to work again, you can do so at a high level.